I started off as a numerical analyst, which people normally call scientific computation these days. I looked at numerical methods for fluid flow, and I was a theorem prover. So I would prove theorems about the numerical methods, that they converged. That is, the problem that they're supposed to model is done with mathematical equations, which you can't solve analytically. So you have computational methods, and you can prove that the numerical method that you've proposed or you're analyzing has a certain accuracy to the underlying solutions of the equations. Well, so this was around the time I was coming up for tenure. There was a realization for me that I could continue doing the work that I was doing, but I would be analyzing schemes that no one would ever use. So it would have been mathematically interesting, but not actually interesting in the bigger context. In North America, when you get tenure, there is a nice opportunity to take stock of your career and think about what you actually want to work on next. It's a long push to get to that stage, and then you can start thinking. So as I was thinking, this project with a local fuel cell company came up. There was a strong support for the collaboration from an industrial math network that was formed in Canada. And at a meeting that I wasn't present, I was elected as the leader of the group. And it took me a couple of years to sort of warm up. I had a colleague I still work with who carried the load at the beginning. And then I just really got into it. It was exciting working with this industrial group. And they would do experimental work to motivate the models, and then other experimental work to validate the models. That was one of the most exciting things in my career, is to have predicted behavior with some mathematics and computational methods, and then see that it actually really, the device really did behave that way. So there is the mathematical theory of the type of equations that describe these phenomena. So they're partial differential equations, differential equations. Often what I bring to a collaboration is my computational expertise. There's a kind of a British style of applied math that uses something called asymptotics, which is an analytic method to give insight into what might be happening with the system of equations that you have. So I got some knowledge of that. And so it's just that sort of general skill set that I bring to those different problems, which from an application view look very different, but from a mathematical point of view, there's a real commonality between them all. One of the things about a collaboration that keeps it going is just that you enjoy working with the other person. But then on the technical side, it is that you have some overlap of expertise, so you can talk about stuff and yet have different skills outside of that. And so, you are close enough that you're not, just staring at each other strangely, not understanding anything that the other person is saying, but appreciating what the other person can bring, the depth of skill that you maybe only kind of half know. So Tim has started a project on modeling cylindrical filters. So these are large-scale filters used to remove contaminants from drinking water or other chemical contaminants from other things. There's various types which I think on the engineering side are quite different, but mathematically they're all quite similar. Again, he has some experimental colleagues, some industries that are in the background, and I'm sheltered from all of that. get to work with him a little bit on the modeling, but it's the computational side that I've done. And just for them to have something to play with, I have I'll call it a simulator of a column where you can put in whatever mix of contaminants with whatever reactive properties they have with the filter material, and just turn it on and see what comes up. So there's some places like this around the world. I think what makes the CRM a bit different is you have some permanent people here. Other collaborations that I've had have been at institutes where everyone comes as a guest from somewhere, and you're there for a week in a group of 40 or smaller group, and you get to work together. Yeah, it is different. You know, there's this age of electronic communication, and you think, oh, well, we could just Zoom, but it's just not the same as sitting there in front of a blackboard, scratching your head and writing stuff down and having ideas go back and forth in person. And this is the kind of place that fosters that kind of interaction. So it's interesting, when I put the advice to students, it was mainly for undergraduate students. And I was motivated after an exam that I gave in a relatively small third-year class. And after the exam, one of the students came up to me, a young woman, because they're all young to me now, and she was shaking. And she said she hadn't slept all night and she hadn't eaten, for the last 2 days because she was getting ready, too nervous to eat, getting ready for this exam. And I just thought, that can't be the right way to succeed in an exam format or whatever you're trying to do. So it was advice that was intended for undergraduates, but looking after yourself mentally and physically is one of the best ways to be more productive.